Hi, in this video, we want to take a look at principal component analysis. All right, so principal component analysis, the big idea is that we are going to try and change the coordinate system of our data so that we have a better coordinate system than what we get by default from our data as is when it gets to us. All right, so try to think about this in kind of a three-dimensional space. Think of it as I'm representing my data with three-dimensional space with a bunch of data points floating around 3 dimensions. All right, now what I want to do, I've got a bunch of points floating around in three-dimensional space, and let's say the points kind of go like this. Kind of try to imagine this with me. And what I want to do, I want to find the straight line through that cloud of points that best approximates that cloud of points, but it's only a straight line, one straight line. So then I've got the points like this. So you can see with how I've moved my hands, a line going from here to here would be probably the best approximation I could possibly get. Okay, so that's going to correspond to our first principal component. All right, so what we're going to do is I take that line, I'm going to find a vector, a data vector that is parallel to that line, and that is going to be our first principal component when we pull them out. So that will be called the score or the X, depending on which function we use within R. Okay, but wait, there's more. Because for every single column of numeric data I have, I can get the same number of principal components. So here I'm talking about three-dimensional space. That means I can get 3 principal components. Okay, so here I've got, think about it, I've got a cloud of points floating here. There's a line, if I draw a line here, that is my first principal component. Well, what I want to do, I want to find the line that is perpendicular to that first line. I want to find a perpendicular line that goes through the rest of the cloud as well as possible. And that will be our second principal component. So once I find that line, so it's going to be perpendicular to the first, or orthogonal for those of you who have a stronger math background. If it's orthogonal, then it passes through the cloud as best as possible, best representation I can get by one line that is perpendicular to the first one, then that is going to be my second principal component. All right, now the third principal component is the line that is perpendicular to the first and the second and best approximates the rest of the data. Okay, so this is kind of a weird concept, but let's take a step back and let's think about something kind of related in statistics. When I start looking at summary statistics, if I have the mean is a 1-number summary of my entire data set, right? Right? That's what it is. If I take the mean and the variance, that's a 2-number summary of my data set of a univariate statistic. Okay. Now, those are just for individual variables in our data. What principal component analysis does, this kind of gives us a summary of the entire numeric data set. So that's a lot. That's going from, in real life, if I have 10,000 variables and I can get the first principal component, I am summarizing 10,000 variables with one vector. Now, still hard to interpret, still a lot of things to it, but it's a good approximation. Okay, that's interesting. And so if I take the first and the second, I have a better approximation. If I take the first, second, and third, I have a better approximation, and so on. Now, what's going to happen when we talk about principal component analysis is that we get diminishing returns. So I don't want all of them. I only want a few of them. For most applications, we're going to need, for the work that I do personally, most of my variables are below 30 dimensions. So probably around 2, honestly, covers as much as I need. We're going to talk about what we need to do to determine what works best for us. Now, why do we want to do this? All right, well, for one, I can replace my data with a few principal components. So let's say I have 10,000 columns of data. That's too much for me to deal with. It's just too much, man. I can't deal with it. So I'm going to take a fraction of the number of principal components, and that I'm going to pretend that that is my original data set, and that's the one I'm going to use. We can also use principal component analysis to analyze our data in something called factor analysis. That's very useful. Another thing that we can do for it is, once again, outlier detection. So if I start plotting, remember when we plotted our clusters previously, we used the first two principal components we plotted, and then we went, hey, that point over there, that doesn't look like the rest. And that's a way to do outlier detection also. And there's times for all of these methods. Whatever works best for you for your project is what you should be doing. All right, so for this video, once again, I'm going to use the decathlon data set from the cluster var package. All right, so something that is important when I do principal component analysis is I have to scale my data if I have like widely different standard deviations, or they're on different scales. The main consideration is the comparative size of standard deviations. Honestly, if you start like reading through the literature, they're going to a lot of the books and the papers and the blog posts online talk about like units of scale and stuff like that. Like, honestly, look at the standard deviation. If one of them is like way bigger than the rest, or a few of them are smaller than the others, and you don't want them to get muted out, rescale your data. There's advantages and disadvantages to this, and I'm going to talk about one of the disadvantages later. So I'm going to rescale my data. Now, I'm going to do something strange, and I would only do this because I'm teaching this one aspect. Down here on this step, I'm going to explain why I do this in a moment. I take all of the speed events and I switch their sign. So I make it so that basically, if you're super, super fast, you have a bigger value. If you're super slow, you have a smaller value in the data set. Why do I do that? Well, let's think about what is a good speed in a race? A very small number. Let's think about the jumping events. What is a good result? That is a big number. All right, let's talk about the throwing events. What is a good result? That is a big number. So you can see that I've got, for speed events, you want small, but for the jumps and the throws, I want big. All right, so they're kind of like pointed in the opposite directions in kind of like what's good, what's bad. So just to kind of make things easier to interpret in a moment, I go ahead and I switch the sign on the speed ones. All right, so when I rescale my data, what's going to happen is that a large positive number means it's a more competitive outcome on the decathlon. A negative number, a large negative number, is going to be a very poor outcome compared to their competitors. And so when we look for a moment, it'll be easier to interpret what's going on. In base R, we have two major ways to get the principal component analysis. We have PR comp and we have prin comp. PR comp is the better one to go with from a numerical calculations point of view, because it uses singular value decomposition instead of eigenvalues of the covariance matrix. Now, honestly, you don't need to worry about that, because in data mining, we just need the output. We care about good, solid predictions. We actually don't really care about why it works. We care about predictions. We are working on being like crystal balls for somebody else. Prin comp, that is a better way to go if you're going to be doing factor analysis. If you need to do interpretation of your principal component analysis, you're going to be doing factor analysis, and prin comp is a better way to go. Honestly, I use prin comp at work because I don't do very much factor analysis very often. And most of the time I can extract what I need from prin comp anyway, but do whatever works best for you. All right, so I'm just going to go with PR comp on this. I'm going to go ahead and compute it. Okay, so the first thing I get out of my principal component analysis is the standard deviations. Okay, so I got 1.8, 1.3, 1.2, 1, 0.8, 0.8, 0.76, and so on. Okay, One thing that should jump out at you about this is that these numbers are decreasing. These are getting smaller and smaller and smaller as I go from first to the end. That will be the case every single time. The first one will be the biggest, the last one will be the smallest, and it's going to decrease along. So the standard deviation, this is how we measure how important a principal component is. The bigger it is, the more likely I want to keep it in my model. Now, the next one are these rotations. All right, and this got split off, which is going to make this next part kind of difficult. So I am going to try to do something. All right, let's move a little bit down. Okay, the rotations tell us our interpretation of the principal component analysis. Now, this gets very, very tricky, and I've had trouble explaining this to people in the past. So bear with me for a moment. The first thing you want to do is focus on the first principal component. And if you can interpret that, good, move on to the next one. Basically, keep on interpreting until you get a principal component that doesn't make sense to you. Once it doesn't make sense, then you go, okay, the rest of these are probably small enough that it's not that important for me anymore. The most important one to interpret is the first one. Second most important is the second one. Third most important is the third one, and so on. Okay, I want you to notice that all of these have a positive sign. Remember, bigger is a better value in this data set because of that sign switch I made. So positive, it's kind of small, positive, 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 kind of small, positive, positive, positive. Okay, how I interpret this is the first principal component is an overall measurement of the athlete's competitive ability. Because basically, since it's always positive, a bigger value means that they get a bigger principal component for all of the events. So that means that they get more points, they get a higher ranking, they are more competitive. Now, let's move on to the second principal component. First thing you want to do when you do this is you want to look at the sign of the loading coefficients. Okay, so I see that I've got negative, 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 and negative. Okay, so I can see that 100 meter, 400 meter, 1500, the hurdles, long jump, and pole vault all have negative values. Now for high jump, javelin, shot put, and discus, they're all positive. Okay, so first and foremost, we can see that the speed events all have negative sign. We can see that the throws all have positive signs. Now, let's think about high jump. I mean, you use a lot of hip power when you do high jump, and you use your hips a lot in the throws. So the data is saying that the high jump and the throws go well together. Now, pole vault and long jump, those are also very, very important speed events. Those are ones where they're going like crazy fast going into the jump. So what we can see here is that this is kind of partitioning the data into the fast, the faster athletes, and the more of the thrower athletes, high jumper athletes. So think about like back in the, when you talk to people, you're like, oh, I'm an English person, or oh, I'm more of a math person. You hear people talk about that. Well, honestly, when you start talking to these people, you realize that usually, if they suck at math, they usually suck at English. If they suck at English, they suck at math. Honestly, that's just how it is. And well, in that first aspect with they suck at math, suck at English, that's like their first principal component is showing like what is their overall academic ability. Now, the second principal component is kind of measuring where are they better, where are they weaker compared to the others. Like grouping the events together, grouping the subjects together, where are they on a spectrum? Overall, they tend to be together. That's why the first principal component goes with all of them. But the second gets a little bit more nuanced. Like, yes, there are people who are faster and there are people who are more throwers and who will have like equal ranking, equal points overall. Now, the third principal component, I'm going to look at the negative values first. 400, 1500. All right, so our longer distance speed events, then high jump, javelin, shot put. Javelin, shot put, high jump, long distance. It's not jumping out at me. Now let's look over here. We have sprint, hurdles, long jump, pole vault, and discus. Discus is kind of thrown out. All right, so I'm having trouble kind of interpreting this. So what I'm going to do, I'm going to go and I'm just going to remove the smallest values until either I feel comfortable with the interpretation or I conclude it's not worth worrying about any further. So I went through and I got rid of all the ones that had a 0 after the decimal. So now we have 100 meter as positive, long jump, pole vault. So those are speed events. We have long distance, high jump, javelin. Okay, so how I interpret this any further is if we want to go even deeper, if we dig deeper into our principal component analysis, the second one, it gets more nuanced when I go with speed versus basically everything else. So yeah, so here we've got speed and speed events, because you have to be running crazy fast, and pole vault requires that sprint down the runway. And then here we've got distance and throw put together. So we can see like here we've got speed sprinting, and then we have long distance and throwing getting put together. So this is getting into more nuance than we had for overall speed along against all of the throwing events. Okay, and usually once you start like having trouble interpreting something, usually you want to stop. I'm going to go ahead and just kind of dig in. See if we have anything interesting. 1500 hurdles. So speed and long distance in opposite direction. This is, yeah, I'm not really seeing this. If I wanted to dig in a little bit deeper, I could go ahead and get rid of like one more, see if that I can interpret that. I'm not seeing anything. So I'm going to go ahead and just stop. My conclusion, honestly, if I want to use this, depending on the type of model, first principal component is like their overall global ability. The second principal component is telling me like roughly, are they like speed people? Are they throwing people? And then third principal component is kind of breaking that second one down a little bit further. But yeah, I would try to avoid this. I might use this if it was underneath the hood and I'm not gonna have to explain my variables, then I would be very comfortable using these later ones. But if I have to explain it, I definitely won't go past the third. All right, something to talk about when we talk about principal component analysis is that we get these values from some linear algebra, some matrix algebra, and that's really important, really interesting. If you want to start digging in, if you're a PhD student, you really need to understand this aspect. But for this class, we just want to be able to make good predictions. This is a predictive analytics class. That is what we care about. So I'm not going to worry about digging into that any further. One of my PhD exams was on that topic. All right, so now if I hit summary on my principal component analysis, I can see the individual standard deviations. I can get the proportion of variance that each principal component gives that corresponds to how long the line is in that data cloud. And then the cumulative proportion tells me how much I would get if I just use, let's say if I use the first 3 principal components, I've got 64%. Now, because this is a decreasing number, decreasing sequence of numbers, we get diminishing returns as we go to the right. You notice that here we get less than 2% as we go from left to right. Here we get about 4% as we go left to right, and then about 5% as we go from left to right. And we get the most gains early on. All right, now this next part, the str function is to examine the structure of an object in R. All right, the important aspect on this, the reason why I'm showing you this, is this little line right there. Okay, if I want to do dimension reduction, I want to use a principal component as a predictor variable in my model, I need to use this X part. So I would use PR_comp M, because that's what I call my principal component analysis model, $X. That gives me that gives me 10 new variables that I can use. First column, it goes with the first principal component. Second column goes with the second principal component, and so on. And so here is the head of the function, or head of the score values. And so we can see where these guys are landing. Now, something I did with the data was I did sort it so that the stronger athletes were the ones with the better points were at the bottom of the data set. The athletes with the weaker points were at the top of the data set, just so that it helps me interpret what's going on. And I see the negative values at the top. That's consistent with what's going on. That helps reassure me that I'm executing what I want to execute. All right, so now let's go ahead and start doing some visualizations. Visualizations are going to be a big part of the rest of this video. So here, this is a bar plot to show how the principal components standard deviation, or excuse me, variances, how the variances decrease. So we can see from 1 to 2 is a big drop, then something of a drop, about the same amount of drop, and then it kind of flattens out. So that's the default plot function. So why do we care about this plot? This plot helps, so we've got 3 different criterias to choose how many principal components to use. First one is I want the proportion of variances to be above a certain threshold. And then basically it's above a certain threshold, I'm going to keep it. Next one is that we want the cumulative proportion of variance to be above a certain cutoff. So I've seen 90 and 0.9 and 0.95 as being the cutoffs for these. If that works for you. Another one is to go ahead and just take any of them that have a proportion of variance greater than or equal to 1 or greater than 1. Now, this has a very solid geometric interpretation. This makes a lot of sense if you've got a stronger matrix algebra point of view. But if you have rescaled your data, my opinion is that this 1 cutoff is not a good way to go. I would not use it if I rescale my data. I would use it if I did not. And that comes from some, just matrix algebra aspects. So, if you want to get into that, that's beautiful, but we're not going to talk about it any further. All right, a scree plot. Scree plot is really the same thing as the default plot. If I run these on print_comp, it'll give me axis labels a little bit better. All right, now we want to talk about biplots. And the biplots gives us 2 things to represent. First one is it shows where the individual observations are in a scatter plot on the first 2 principal components. And we can have different principal components used in the visualization, but usually the first 2 are the most important. Also, as an added bonus, this tries to show us how much each variable contributed to the principal components that are in the visualization. Now, because of our markdown, it's hard to see what's going on. We're going to get into some better visualizations in a moment. But you see with all the black values, these are the athletes' names of the individual observations. So we can see that, was it Karpov is far to the right. So that shows a very competitive athlete. We can see that the athletes over here are less competitive. Now, second principal component, that tells us where they are on the speed and thrower spectrum. So this athlete is going to be either really fast or a very strong thrower, but weak on the other. Drew's is going to be either really fast or a really strong thrower, but will be weak on the other events. And so this axis tells us how competitive are they overall. This one tells us how much of a specialist athlete are they. Up and down tells us how well they are as being a specialist. Now, remember that when I do this, I've rescaled my data. So then when I'm looking at this, you know, I can interpret this in terms of standard normal magnitudes. Now, the GG Fortify package gives us a nice way to plot the points. I don't really like these special GG packages, honestly, the ones that break away from the grammar of graphics conventions. I just avoid them, but here it serves a purpose and it does a good job. So here, what we're going to do, we're going to make a scatter plot of the first two principal components, and we're going to color the points by the number, color the scatter points by the number of decathlon points they earned. So the bigger number means that they are more competitive. Let's take a look at what happens. Okay, so when we look at this, so here I've got a scatter plot of first principal component along this axis, second principal component along this axis. We can see that about 33% of the variance is accounted for by the first principal component, and then about 50% is accounted for by the first two. Now, look at the points. Okay, so the points in the decathlon corresponds to the color scale over here. And you'll notice I've got dark here, it gets lighter, and I've got light here, dark to light along the first principal component. This confirms what I concluded earlier, that the first principal component is measuring how solid of an athlete are they overall. Whoops, went a little bit too far. The Facto Extra package gives a lot of tools for working with principal components. It's really nice. It's pretty slick. So the first one is to look at the eigenvalues. And eigenvalues correspond to the standard deviations or the variances. Yeah, of course, there's a square root difference. They correspond. All right, so we can see that it decreases like this. Makes it a little bit easier, uses a steel blue color to look at. That's nice. All right, now what I want to do, I want to plot the individual observations in my principal component analysis, and the COS2 parameter, this is going to say color the points by how well it fits my model. So if I have a more extreme value, it doesn't fit the model as well as other points in the data. All right, so when I see this orange color, this is telling me that this data point does not fit the model as well as other data points. When I see this cool blue, these points fit the model better than other data points. So this kind of gives me a feel for what's going on. I can see that it looks kind of circular as we go out. The farther out we go, the less it fits. Nothing's really jumping out at me as being horribly bad. If I saw like a super, super, super dark color that was very different from the rest, I might consider omitting that point or imputing its values. Now, this function goes through and this takes a look at how much does each individual vector, each individual variable, that's what the var does, how much does it contribute to the overall model. and I use contrib to pull out the contribution aspect. Okay, so first thing I want you to look at, I want you to look at it from a left to right point of view. Left to right, left to right. Don't go up and down yet. Left to right, left to right. I look along this and I can see that the farthest one to the right is like my 100 meters and my, we've got shot put here. We've got 400 meters. But so like the farther to the right, the more important it is for that first principal component. Okay, so if I'm interpreting the first principal component as measuring the overall athletic ability, we can see that these are having a big impact in that measurement, but javelin, pole vault, and 1500 are not having much of an impact on this. So let's think about pole vault. Pole vault is probably the most technical event in track and field. And so it's one that it's going to be hard for a lot of people to practice. And so that might just be, access to a pit to be doing pole vault on rather than a person's athletic ability. Okay, javelin, once again, people aren't going to be too thrilled if you're throwing javelins in their yard. That thing goes pretty far when you compare it to like a shot put. It's going to be harder to practice on your own. 1500 meter is the longest running event of the decathlon. And so if you think about 100 meters, 1100, 110 meter hurdles, long jump, these are all like intense sprinting. And this event doesn't really, fit with the other events. And the 400 meter is also a sprint. It's a very painful sprint, but it is a sprint. Now let's go up and down. Let's go up and down. All right, so when I go up and down in this hemisphere, what this is saying is that these are kind of like a group of variables. This is a group of variables down here, and they're measuring different things. So as a group, this is kind of measuring that throw and explosive hip aspect to being athletic. This is measuring a speed aspect to being athletic. And here we can do a biplot where it puts them on top of each other. And they like to get overlaid with each other. I think this is best to not really look at. If you have a lot of data points, it gets to be too many. But if you feel like you should probably plot it, take a look, and throw it out if it doesn't work for you. That's how we normally do data science. Run it, take a look. This works. Oh, this doesn't, throw it away. Okay, so let's take a look at this. Here I've got my eigenvalues. So one of the criterias for keeping a principal component is that the eigenvalue is greater than or equal to 1. Another criteria is the variance percentage overall. Another one is cumulative variance percentage. So one that I've come across is that you want to go until you get 95%. So in that case, we would be using 8, which would not be much of a dimension reduction. Another one I've come across is that you want to go until you get 90, which would put us at 7. So, that's. I usually take the point of view that under double digits for the variance percent is probably not worth using if I'm doing dimension reduction. But whatever, it's whatever works for you. Now here I can pull out the individual aspects for the variable analysis, and here we have the coordinates. If I want to look at how they're relating to the original variables, I can look at the correlations between the variables and their principal component dimensions. We can look at how well the model fits for each of the variables, and we can look at the contribution of the variables to the principal components. And I just kind of print this out so you can take a look. Here's the correlation, and here's how well the model fits for particular variables. how much they contribute. Now here we can do pretty much the same thing, but on individual observations for the coordinates. This is going to be our new data that we use for predictor variables. If we want to do dimension reduction. COS2 is how well does the observation fit within the model, and then this is the contribution of the observation to the model. And that's all I got. Hope you enjoyed the video. I hope you're staying safe. Take care.